This reaction, which I'm just going to show real fast for, effect basically, is called the Thermite reaction. It's a very exothermic reaction. It's very spontaneous. You do have to kind of activate it. You have to get over that energy of activation barrier. But boy, once it goes, thermite is really powerful. Thermite reaction is one way to make elemental iron. All right. It's interesting that people do that. You can see the amount of energy was released. They had a whole blast shield and all kinds of stuff up there. It's a very exothermic reaction. So they added just a little bit of glycerin in this case to kind of activate the reaction. And man, it takes off. And you end up with a lot of energy. Thermite is sometimes used in movies as they're going to make a bomb or something like that. And they use thermite as an example of that. I don't know enough about explosives to know if that's legit or not, but it is kind of an interesting. And we can definitely say that, first of all, it's very exothermic. And because it's occurring, like you can see the bam part right there in the picture, that means it's also spontaneous.
In the center beaker is water at room temperature. To this we add solid ammonium nitrate. The ammonium nitrate dissolves. Usually, a reaction that occurs so readily is exothermic, but we see from the thermometer that this reaction is endothermic. The temperature of the water drops significantly. This reaction is not favored energetically, yet it still occurs.
Reactions that are exothermic, energies released, are certainly spontaneous. They definitely happen. And again, up till this chapter, we've always assumed that it was only exothermic reactions that are spontaneous, that occur. This is an example of a reaction which is nowhere near as cool, in my opinion anyway, as the thermite reaction. But what it's showing ammonium nitrate dissolving in water, all right? And woohoo! I know you're excited by that one. Wow, I can go take table salt and put it in water. Woohoo! Anyway, why this is cool for this discussion, all right, is that it dissolves, all right? And you're like, okay. Why it's interesting that it dissolves is it's an endothermic reaction. And you could actually see there the temperature decrease. It started off at 23 or something and went down there to 11.6 or so. So this is an endothermic reaction, but the stuff is dissolving, all right? And if it dissolves, that means it's spontaneous, okay? So this is an endothermic yet spontaneous reaction. And so obviously enthalpy is not enough here to understand why reactions are spontaneous. We need more than enthalpy to understand spontaneity, and that's what we're going to start looking into. So this reaction, again, not anywhere near as cool as thermite and, adding sodium to water, these kind of things. However, from an intellectual perspective, this is a fascinating reaction because it's endothermic, yet it's occurring. It's spontaneous, yet endothermic. So what we're going to do now is look at the rules used to explain really what spontaneity is all about. To understand why spontaneity is about more than enthalpy, we need to introduce entropy. And entropy is one of the most fascinating of all ideas in chemistry as far as I'm concerned. Now, we talked about how energy dispersal and mass dispersal kind of help make reactions spontaneous. Well, energy dispersal is related to enthalpy, all right? So exothermic would be energy dispersed and stuff like that. On the other hand, if you didn't have energy dispersed, it would be endothermic. Entropy is related to the mass dispersal part, and entropy is really a measure of disorder. It's a measure of randomness. If you have things that are very organized, you are not helping entropy. I always like to tell people that if you're a person that doesn't like to clean up your house or your room and stuff like that, hey, you're helping entropy. Woohoo! And that's really dumb. And, if your parents or whoever get mad at you for not cleaning your house, then please don't use thermodynamics as an excuse. However, spontaneity is related in its own way to entropy, to disorder, to messiness, all right? And there's a lot of philosophical implications that come out of entropy that aren't necessarily as obvious when it comes to enthalpy. So entropy is given the symbol S, capital S, and it is related to mass dispersal. So going from a very organized mass, concentrated mass, to a more distributed, i.e. messy and random state of matter. Entropy started with Boltzmann, and on his headstone back there, it said S equals K times the natural log of W. And W is the microstates of a system, and we'll talk about what that means in a little bit. And the number of microstates, the more places it can be, are related to the entropy. It's entropy equals the Boltzmann constant K times the natural log of the microstates. You don't need to use this equation because this isn't very helpful for us, but I wanted you to know where entropy originally came from. K is that Boltzmann constant. There's the actual number. No, you don't need to memorize it. We're not going to use this equation. However, what is important here, if you have fewer microstates, you'll have lower entropy. And if you have more microstates, you'll have higher entropy. So imagine if you have all of the pencils in your house in one drawer, all right? Well, you could have the pencil with the lead facing left or right, and those would be microstates, but there's probably not too many. On the other hand, if you take those pencils and you throw them around your room, oh man, now there's all kinds of these places, these ways that pencils could be. They could be, perpendicular to where they were held before. They could be stuck in the ceiling. They could be in the garbage can. You could put them down the garbage disposal. I don't know. There'd be lots of different ways you could put those pencils in your room. And the ways that the pencils can be in your room is this microstates, which is really weird, I know. The more microstates, the more ways you can put the matter around, that means you're going to have more entropy. So what this is saying is that if you have an organized matter source, you're going to have lower entropy, fewer microstates they can be in. On the other hand, if you have lots of disorder, lots of possibilities for where the different pencils can be, then you're going to have higher entropy. All spontaneous endothermic processes have an increase in entropy. Entropy is enough to kick the reaction to the spontaneous level, even if it's endothermic. We're going to see that enthalpy and entropy sometimes kind of like fight for if a reaction is going to be spontaneous or not. Sometimes enthalpy and entropy both want a reaction to be spontaneous, and sometimes they fight. And sometimes neither one of them wants a reaction to be spontaneous. So we're going to see here that enthalpy and entropy can work together, and they can work against each other. We'll talk about how to figure out when it does and when it doesn't. This is a reaction showing an atom A, two atoms A and B, and atoms A, B, and C, okay? So bear with me. And in this different scenario, we've got a two-flask system. Now, focus with me just for a second on if you have just atom A. Well, if there's two flasks, atom A could be on the left side, or atom A could be in the right side. So that would be like two microstates, all right? And they take the number of microstates and they raise it to the number of atoms to figure out. So in the first case there, with just one atom in a closed thing, you'd have two states. On the other hand, if you have two atoms, A and B, then there's four possible microstates, all right? So you can see A and B could both be on the left, A and B could both be on the right. You could have A on the left, B on the right, or you could have B on the left, A on the right, four microstates. And then it gets more complicated. So you can can see that 3 atoms has a lot more states. You can imagine the 4 would be even more. You basically take 2 to the number of atoms. So now imagine if you had 6 times 10 to the 23rd, 2 raised to that power. Goodness, that's a lot of different microstates. So entropy can get pretty crazy pretty quickly, all right? And again, we're not going to do that much with microstates, but I want you to see kind of what they're thinking. With pencils, I was arguing, yeah, you could have pencil on the ground, pencil on the table, pencil stuck on the ceiling. I don't know. Those would be microstates of pencils. This is a better chemical example that shows the possibilities. And again, this is just for two different like flasks, all right? If you had 3 flasks or 4 flasks, it would be crazier. Entropy can get pretty crazy. But when all is said and done, entropy is about disorder. And the more possible states you have, the higher disorder is possible.
Molecular motions are much more random in the gas state than in either the liquid or solid states. Motion in a liquid is more random than that of a solid. Gases tend to have the highest entropies, while solids have the lowest.
Entropy is actually a quantity that can be measured, all right? And I'm going to talk about here now some of the factors that affect the entropy values you might see. This is an example of water's entropy, but in 3 different phases. We're seeing water as a solid, which would be ice, of course, liquid water, and gaseous water. And those numbers there represent entropy values. So ice water would have an entropy of 47.91 joules per mole Kelvin, liquid water the 69 number, and gaseous water the 188. So notice here, and this is a trend you see all the time, solids always have less entropy than liquids, and liquids have less entropy than gases. Now solids are very locked in place. They don't have a lot of microstates possible, all right, because they're stuck next to each other. So solids have fewer microstates. Liquids, on the other hand, the connection between them isn't as strong as solids. Like solids had stronger intermolecular forces in Chem 222. Liquids do have an intermolecular force, but it has a lot more flexibility. And flexibility allows for more microstates, more places for them to move around. Liquids have higher entropy than solids, but gases have no intermolecular forces on them at all to any reasonable sense. Gases can go all over the place, so gases have tons of microstates they can be in. Gases have the most entropy. So again, solids always have less entropy than liquids. Liquids have less entropy than gases, and we'll talk about those numbers here more coming up. Only pure elements in perfectly formed crystals at 0 Kelvin have 0 entropy, all right? And this is the 3rd law of thermodynamics. And what it's saying is that basically, in a nutshell, you're never going to have 0 entropy. You're always going to have a positive entropy for a substance. Unless you have that pure elemental crystal at 0 Kelvin, which has so many problems with it, as you can probably imagine, it's going to be crazy. That's the only time you could have 0 entropy. So basically, the 3rd law says that all substances will have an entropy greater than 0. And you can see there that solids are closer to 0 than liquids. Liquids are higher, gases are higher. So the individual entropies of substances will always be positive numbers, and that'll be important here coming up. There is an entropy guide if you're curious more about what's going on here. So here's a question. Which of the following will have the highest entropy at 25 degrees Celsius? Okay, well, there's a whole bunch of different things there. Notice here, though, what's important is that you have solids, liquids, gases, and unobtainium, by the way, is the false element they were looking for in the Avatar movie, the movie Avatar, when they're on that kind of jungle world, not the TV series. But anyway, I digress. Unobtainium's just a joke, ignore it. Anyway, if we answer this problem, sorry, prof hat back on, whatever. To answer this question, there we go. What we want to do really is look at the phase of matter, because remember here that gases have more entropy than liquids, liquids have more entropy than solids. And good old xenon there, xenon is a gas. And usually the phase of matter is the most important thing to consider when talking about the entropy. Xenon gas has the highest entropy by far. Gases are always higher than liquids, liquids are always higher than solids. And unobtainium is just my poor excuse at a joke. So anyway, when it comes to highest entropy, gases will always be higher than liquids. Liquids will be higher than solids. Here's just some examples. Bromine, it's normally a liquid, but it has appreciable vapor phase over it, which is like a gas phase. So we would say that liquid bromine has a lower entropy than gaseous bromine. On the right is an example of water as an ice. Obviously, that nice piece of ice compared to the liquid water, we would again say that solids have less entropy than liquids. I did forget to mention that that little zero mark over it, that means standard states. So you're talking about standard versions of things, not, like next to the sun or in a vacuum or something like that. You'd have 1 atmosphere of pressure, blah, blah, blah.
Heptane at 1500 Kelvin has significantly greater molecular motion than it does at 200 Kelvin. The substance has greater entropy at 1500 Kelvin than at 200 Kelvin.
Compounds, their entropy is affected by temperature. And if you look at the units of entropy, they're always joules per mole Kelvin. Entropy is absolutely affected by temperature. And so in this example, you have a heptane at a lower temperature and a higher temperature. And the lower temperature, you have lower entropy. Higher temperature, you have higher entropy. And that's very common for all substances. I like to think about this as if it's cold outside. Like if it's cold outside, I'll go out and I'll be, I won't feel quite as energetic, but I do go outside and yeah, it's nice weather and stuff like that. And then I'm more excited, more energetic. All right. Well, this applies to entropy as well. Entropy in this context, that would be more about like vibrations. It's vibrating more. It's rotating around more, stuff like that. It's having more microstates, basically. You're making the matter do things that it would be easier at higher temperatures than it would be at lower temperatures.
In general, the more complex a molecule, the greater its entropy. We can see this trend by comparing 3 alkane molecules. The amount of motion for each molecule translates into entropy. The more motion overall, the greater the entropy.
As molecules get more complex either through number of atoms or just even molar mass, generally the entropy increases. So in that video, it compared methane to ethane to propane, 3 of the alkanes we talked about in organic chemistry in Chem 222, and you can see their entropy values are increasing. So as the number of as atoms in the molecule increases, the entropy increases. You have more ability for those little atoms to have microstates moving around and stuff like that. This also applies though to molar mass, and this is an example of a bunch of noble gases, and they're all gases, so they're all gas phase. But notice how the entropy increases, and that's mostly just a factor of them having more mass. And so the individual, you can think about individual electrons or protons are moving around. I mean, they're still all gases. They still have high entropy, but xenon has the highest entropy of all because it's the biggest, and helium would have the smallest one. So molecular complexity and molar mass are certainly related to increases in entropy as well. Entropy is really fascinating, especially when compared to enthalpy.
The entropy of a solid depends on the strength of the forces holding it together. The weaker the attractive forces, the greater the motion of the ions in the crystal lattice, and the greater the entropy.
In Chem 221 and Chem 222, we use Coulomb's law to justify why some atomic bonds were stronger and weaker, and we talked about the distance between ions. But the part that's important here is that we also saw that the number of charges on the cation and anion do affect the force connecting the 2 atoms together. And this has an effect when it comes to entropy. Now, if you look at MgO and NAF there, MgO has a +2, -2, all right? And that's like 2 handshakes holding on to each other, we talked about in the earlier classes, and those are stronger bonds, all right? It's harder to break up a +2, -2 than a +1, -1. So +2, -2 combinations of ions actually are stronger. They don't go around as much. They don't have as many microstates. So MgO has a lower entropy than NAF. And the rationale is that sodium fluoride, a positive one, negative one's like a single handshake. And I said, hey, what's going on? I haven't seen you. And someone says, oh no, break it up. Well, it's pretty easy to break up a single handshake. However, if you have a double handshake, I haven't seen you forever. Well, someone wants to break that up. It's harder, okay? Entropy doesn't do as well when the forces between the ions get stronger. So you can see positive 2, negative 2, smaller entropy, not as much flexibility, not as many microstates possible. If you had a positive 3, negative 3, for example, aluminum nitride, ALN, that should have an even lower entropy probably than positive 2, negative 2, MgO. So all of these things are affected when it comes to entropy considerations.
When potassium permanganate dissolves, its crystal lattice is broken apart, leading to an increase in disorder, and therefore an increase in entropy.
Usually, and notice my emphasis there on usually when you put a solid in a liquid in a solvent to make a solution, usually the entropy increases, all right? Because you are taking that nice concentrated ionic lattice, putting it into a pure solvent, making a bunch of ion dipole forces inside, breaking up things. So usually entropy gets bigger. This is the weakest of all these assumptions though, and we're going to see in lab some exceptions to this rule. I'm letting you know. But overall, if you have to guess, making a solution will increase the entropy relative to the pure substances. Which of the following would represent an increase in entropy? Okay, first of all, freezing of water. So taking liquid water and turning it into a solid. That would not be an increase in entropy because liquids have higher entropy than solids, which is what you're turning it into. So that wouldn't be a good example. On the other hand, if you take boiling water, liquid water turned into gaseous water, hey, that's a change of entropy. Liquids going to gas, that is an increase of entropy. Gases always have more entropy than liquids. I would say the answer B is correct. Now, let's look at C and D real fast. C, crystallizing a salt. All right, well, if you're crystallizing a salt from a solution, then the solution, you had all the ions running around, and making a crystal, everything is nice and ordered. That's not going to increase entropy. And D is also worth commenting on. You have 2 molecules of NO going to 1 molecule of N2O2. 2 molecules to 1 molecule, that's becoming more ordered. And you can think about that as like cleaning up your room. 2 pieces to 1 piece, matter was being distributed and dispersed, and now it's very concentrated. That's also not going to be entropy favored. It's not going to be an increase in entropy. In this problem, we're talking about increases in entropy when a change occurs, a change in entropy. And that's kind of a fascinating thing we're going to start getting into. But I want you to start thinking about factors that will change, that will affect an increase or decrease in entropy as the system changes.